So what is law of constancy of interfacial angles? We know that two faces or any two adjacent faces are joined together by some angle. That is, there is some kind of here angular thing which binds my two surfaces or the two adjacent faces. So this law states that angle between adjacent corresponding faces is interfacial angles of the crystal of a particular substance, and it is always constant irrespective of how it is being growing or what is the size and the mode of growth of crystal. For example, see, here we have three different structures. They are having different sizes, but the angle between two adjacent, which is being denoted by theta, is always 90 degree. The shapes are different, the sizes are different, the mode of growth is different, but the angle is same. And the instrument with which we measure this interfacial angle is known as goniometer, which is shown here. Then the next law comes is the law of rational indices. This is what a Miller indices is. We all have heard about Miller indices. So what this law states? It states that the ratio of the intersects of different faces of a crystal with the three axes are constant and can be expressed by rational numbers. And the three intercepts of any face of a crystal along the crystallographic axis are either equal to unit intercepts or they are some simple whole number of multiples of them. They will never be in a decimal thing or in a fractional thing. They will always be a simple whole number. So now the third law is the law of constancy of symmetry. So this law states that all the crystals of the same element have the same symmetry properties. That is, what are these symmetry elements? They are the plane of symmetry, axis of symmetry, and center of symmetry. And we should always remember the total number of plane of symmetry, axis of symmetry, and the center of symmetry are the symmetry elements. And the operations which we do on these symmetry elements by rotating it and getting the original crystal back is known as the symmetry operation. So now a symmetry operation is an operation performed on a crystal such that the crystal transformed into a state indistinguishable of its original state. See, these are the two diagrams. This is the axis through which we are rotating. We are rotating it through 90 degree, we are getting this. See, B went off to this position, C to this, D to this, and A to this. So you can see there is the movement of the numbers which is there. This is the way we can rotate them by 90 degrees, 120 degrees, 180 degrees, and 360 degrees. And we can get back the indistinguishable form of the previous one. Plane of symmetry, that is that imaginary plane on a crystal system such that when it divides the crystal into two halves, they are indistinguishable. One half is the mirror image of the other half. So, in this we have two kinds of planes of symmetry. One is the rectangular plane of symmetry, and the other, the diagonal plane of symmetry. Now what are these? This is the rectangular plane. So it is that imaginary plane which is passing through the midpoints of the opposite faces of the crystal, and it is dividing it into two halves. See, this and this is this midpoint through which it is passing, and it is dividing into two halves, this half and this half. But if you see it very closely, these halves are mirror images and they are indistinguishable. So this is what your rectangular plane of symmetry is. Now if I move over to the diagonal, this is again an imaginary plane, and this is going diagonally from front, this edge, to the rear, this edge. And if I see this triangle and that triangle, they both are the mirror images. They both are indistinguishable halves of the same crystal. So that is the diagonal plane of symmetry.